Hello, hi and welcome. Today we're going to do something a little out of the ordinary. So I have been following along with this PlayStation 1 article slash course, and I thought it would be a very good exercise for both me and an interesting video if I kind of explain the stuff I learn in the steps of the course and show the code and kind of talk and show the progress I do. So for this kind of step, I have been writing down a lot of notes during the course, so I thought we would just run through it real quick. So the course, as I said, focuses on the PS1 and development of games to that system. And we use C as the programming language, and we use the PSYQ development kit. The PSYQ development kit is as far as I know, the only official development kit released by Sony. And in 2024 there is a lot of open source community made helpers to get this up and running. In 1993 PSYQ was launched, seems like. So some specs on the hardware side for the PS1 is that it's a 32-bit machine, and it has 2 megabytes of memory, 1 megabyte of video memory, and some co-processors. The co-processors are basically there to help offload the main CPU from having to do all of the work. So kind of like a regular computer where you have the CPU and you have the ALU perhaps, or the GPU, or a video, I guess, or audio chip or something like that. So very similar to a modern day computer. So we have the floating point. No, sorry, that's not in the PS1. We have the GTE. The GTE is a very important one. It handles all of the geometry transformation code. So all of the multiplication of matrices, all the mathematical operations related to vectors and matrices is handled on that coprocessors. And I have this map here to show where it all is. So the GPU here with 2 chips of 512 kilobytes VRAM adding up to 1 megabyte. Over here we have the main memory, I guess, the RAM, which is 2 megabytes, the CPU. Let's see, yeah. So if we kind of fast forward here, we started in the course by doing MIPS assembler code, since it's a MIPS CPU. So we wrote some very basic assembler code for the PS1. So here's some information about CPU. Nothing really that important. It's a RISC CPU, so it has the pipeline thing with the micro instructions, and it orders them in the correct order for Mac optimized speed. And it's a reduced RISC is a reduced instruction set. Kind of stepping forward a lot here. We currently I am the course, and I am learning about how to read from the potential CD ROM disk. Since the main memory is probably not enough for a real game, 2 megabytes is not enough to hold a whole game with cutscenes, textures, game code, audio. we of course need to store that on a disk. The disk on the PS1 at least has a upper limit of 650 megabytes, so that is more than enough, probably for a PS1 game. And it's divided into sectors, as you can see in the image here. But noting here that the PS1 usually only has one of these like big sectors, as far as I understand. And a fun fact about the CD ROM, at least, or at least I didn't know the specifics, is that the data is encoded as a scratch or a reflection. So either it's reflecting light or it's not reflecting light in a series of a pattern, and that represents the bits 0 and 1. And that's probably why if you do a scratch on the CD, it kind of corrupts the data, depending on where you do the scratch, of course. If you do a scratch on the part where the game code is stored, you will corrupt the game, obviously. Yeah, so it's divided into sectors, and sectors are then divided, or it's sections which has tracks, and tracks have sectors. And each sector is 2048 bytes long. And that's the thing, the PS1 has, or the regular thing to do is have one track. So track 1, and in that we store all of our assets and stuff. So it's stored in chunks of 2048. So when we read from the disk, we can only read, we do reads of number of sectors, so we can only read in multiples of 2048 bytes. Yeah. So to like create this ISO file, which is our digital disk, I guess. It's the same thing as reading a disk from file. I created this build bat file. So we use make. So we have two external dependencies. Other than PSYQ, of course, we have Nugget, which is a modern thing. I'm not entirely sure what it does, but it gives us access. I think it's a build tool that helps us compile to a PS1 exe. And then there is the PSYQ IVU, which is fixed headers. Yeah, I think it's a helper for modern development when using PSYQ. And the meat is stored here in the PSYQ. And there's a bunch of header files here. For example, the libgte, which, as we said earlier, the graphics transformation engine. And this header gives us functions, for example, rotate matrix. It has matrix normal. It probably has like matrix, yeah, combining matrices, rotation, translation, scale. So a lot of very useful functions to work with matrices. So I don't know, we shouldn't commit that anyway. Alright. So as I said, we use this kind of build chain. So if I do make, for example, this is the wrong file. Let's go into the correct folder. So if I do make, it builds the game with this make file. It just appends the PSYQ things. Our source files are here, and it adds PSYQ here, and it includes Nugget, and then it builds. And from that we get the file called hello.gpu.psyq here. Sorry. This file here, hello.gpu And from this file, combining this file with this XML file, which is this is like defines how our disk should be constructed. So there are some identifiers, some basic stuff. The license file, which I got from the same person who made the ISO thing, and then we define the main hello GPU.psyq. The game code is stored on the disk. We also store a model file, and we have a system.txt. And the system.txt just defines, for example, where the stack address starts, the event routine. I guess I'm not sure about these numbers, but they need to be defined. And it also defines what to boot. So the main.exe, which is defined here, this is where we boot into. Yeah, I guess you could have multiple exes. I guess for a demo disk, perhaps for a demo disk there would be multiple executables on the same disk, perhaps. Yeah, so after we run make, we do make psx ISO, and we define the CD layout.xml. And so this will first ask us, are you sure you want to overwrite, since I already have a ISO file. Yes, then it kind of constructs the ISO file with the given configuration, and out we get a game.iso here. And this ISO file can then be loaded if you want to. I think you could even flash this to a CD disk and insert it into the PS1 and it would boot, I think. But of course for development we have an emulator, and I use the PCSX Redux. I'm on Windows 10 or 11. This has been working great. So if I open up our ISO file here, and then we boot, start emulation. There we are. We have not right now. We don't have anything on the screen, sadly. I have commented out the render code for now. Yeah, but that's the workflow. And what I'm doing right now here is focusing on. So I have this function here, file read, which opens up the CD reader. It searches for a file with a given name, and if we find a file, we calculate how many sectors does this file take up, depending on the size of the file. And after that we allocate, as I said, we allocate in multiples of 2048 bytes, depending on the number of sectors. And after we have allocated memory for the object to be read, we point the CD read towards the file's position on the disk with this set location at the file position. And then we do a CD read on the, so we can read in multiples of sectors, so we read whatever, maybe one sector into our buffer at double speed, I guess. And this will do it asynchronously, so if we did only this, we wouldn't get the result instantly. It would come in a couple of clocks probably. Then this thread would continue on, so we do this to stop and wait, so this blocks until the current operation is complete. And we have some error handling here, nothing important, and then we return the allocated memory buffer. So this works right now for the model file we have embedded into the CD disk, and it reads the correct number of bytes. And what we are currently doing right now is interpreting the model file into an actual renderable object in the game. So the file, I can show you the file. Kind of, it's very simple. It's all very straightforward. Let's see if we can open this with the hex. Yeah. So this is the whole file. I think it's 100 megabytes, 1 kilobyte. Yeah, so 1,000 bytes. So the file can be read as the first 2 bytes, 0008, means how many vertices we have. So we have 8 vertices, so we read X, Y, Z, X, Y, Z, X, Y, Z 8 times. And then somewhere down here we come to maybe here how many faces there are. So I think this would be a cube, so that would have 6 faces. So there should be a 006 here somewhere. This is a 006. Can we search? Or whatever. Yeah, these are the indices, or the faces. So the faces just define the index of the vertex. So 01 is the first, 002, 005, and it comes in quads, so 4 vertices at a time. So I'm not sure if it's 00, 01, 0002, if this defines the quad. I'm not sure. Yeah. Yeah. But anyway, so this model file is very simple. There should be some color data here as well for the color of the various faces. So we'll see why that is missing. Yeah. But our current goal here is kind of just reading the vertices now from the buffer of bytes we have read from the disk. Yeah, so I will come back when we have done that, and we have rendered the model, and we can go through how that is done. Alright, so now I have finished the loading function for the model, and if I show you how it looks, let's see. So here we have the loaded model from the disk, and what we load is the vertices, so each vertex in the cube. The model also contains the faces, so how each triangle or quad is connected, and then we have the colors for each face, and all of that is defined in the file. So maybe I think it would be nice to show how this kind of works. So as I showed earlier, we have this file read, and this loads the file from the disk, and the file is a binary file, and I also showed this just now. It's the binary file full of the positions, the faces, and the colors in series. So pretty simply, here is the code. This is all of the code that goes through the buffer and kind of converts it into vectors and indices. So for each construct here we have the malloc function. So we allocate in the heap the vertices, the faces, and the colors, and then we just iterate through. So the first thing in the file is how many vertices we have. Then it's all the vertices, so we iterate through, and after that it's a number to indicate how many faces we have. So if there are let's say 2 faces, what each face is constructed by 4 indices, since it's a quad. If it was a triangle it would be 4, but we are using quads. So we kind of multiply the number we get by 4, and then we iterate through, and we convert each face to a short, which this short indicates an index into the vertices array. And lastly we have the colors, which I think is for each face. So there would be this should be this number, and this number should be, it's the same number, and we store it as RGB. And then of course we free the buffer, the file buffer, after we have read all of that into our object struct. Yeah, so the object struct is a global variable right now in the main C file, and it has all of these vertices, faces, and color. It also has the rotation, position, and scale, since each object will have this, of course. So that's pretty much it. And if we go down then to the I guess update here, this is the code that renders the cube or the object. This should be object now. Compute the look at matrix for object. Yeah, so we have a camera object. We have this look at functions. We just point our camera to the object position, and then we set up the object. So using the object position, scale, and rotation, we set up our world matrix for the object. And after that we combine the camera's view matrix with the world matrix. Sorry, so the look at, this is a matrix and this is the object matrix, and then it goes into the view matrix. And the view matrix is the one we use in the actual rendering. And then yeah, so the render is also very simple, really. We kind of iterate through the faces, of course, keeping track of 2 numbers, the I indicating which which face we are on, and then there is a Q which is incremented by 1, so we can index into the colors instead of, because if we did I here it would be wrong. We could do I, and then we could do like I +1 and so forth. Yeah. So it's a flat shaded polygon, so poly F4 stands for polygon flat, with, it's a quad, so 4 vertices. And we set the RGB value of the face here, and then we calculate the actual position of the vertices on the screen. So this will take into account the previously set view matrix. We just feed in the vertices, and then we feed in our polygon F4. So all of these vertices values will get translated by the view matrix and so forth on the GTE processor. Since this function is defined in libgt, it's performed on the GTE processor. So the position values will be calculated and stored in polyf4, and we also get this clip variable back from the function. And as far as I understand it, this value just indicates if it's occluded or not, so if it's behind something. And in that case it will be less than or equal to 0, so we discard the pixel here by doing a continue, so we don't render anything. Yeah, and here we also kind of do the same with the OTC. So the OTC, this is the depth value in the ordering table, which is something the GT uses to render. So we kind of check that we're within bounds of the ordering table, and then we render the primitive with this helpful macro. Yeah, so that's very much it for the render. We also do the rotation. We increment the rotation here by 20 degrees per tick. Remove this. Yeah, so this is pretty much it for reading a file from the disk and converting it to something usable. In this case it was a model file, but this could potentially, we could potentially store like texture files, sound files, I guess that also text files if we have a lot of text in the game, or assets that's stored in text form, or maybe map data. Maybe that's not a thing you do in the PS1, storing JSON. But yeah, so I think the next step in the course now will be to kind of building on this loading from disk. We will load a texture and render a textured cube. Yeah. So that, I think that will be split into another coding session, since I will kind of leave on this note. I will of course commit this code, and all this code is actually up on my GitHub. And if as long as the course man doesn't tell me to take it down, the code will be up to be read. Reading model from disk and rendering it cube. Yeah, so that's it. Hopefully this was a little interesting, and moving forward I think it will be very interesting to see the final product that will be produced. Yeah, bye bye.